Okay, everybody, hello. And I hope you had a great weekend. I hope that you all did something really nice for your moms, because being a mom is tough. So they deserve something extra special. So hopefully you did something nice for them over the weekend. We are back this week to talk about graphing sinusoidal functions. So sinusoidal is our big fancy math word of the day. As it implies, you may think, oh, sinusoidal, you see the word sine, so we're going to graph sine functions. Sinusoidal does not refer only to sine functions, but also to cosine functions as well. And once we get started here and we graph both the sine and cosine function, I think you'll see why, and I will tell you a little bit more about why, but that's our goal today, is to look at the graphs of sine and cosine functions. We're going to talk, there's different parts and pieces of sinusoidal functions. We're going to talk about part of it today, and then we'll continue that conversation in the second video as we build on what we're going to establish here today. So let's start by graphing y equals the sine of x. All right, so I know how much, again, you all love graphing. And I don't expect that you know what this graph looks like, although some of you may already know. But when all else fails and you don't know what the shape of a graph is, then what we're going to do is, you guessed it, we're going to make a table of values. So the answer was not your calculator or Desmos, by the way. All right, so we're going to make a table of values. So let's think about what would be some good choices to plug in for x, right? If we want to evaluate the sine of some x value, then we need to make a good choice for x, so pick something that we can evaluate, right? So let's say that we could start with 0, right? Because we know that the sine of 0 is what? So this is going to make sure that you know all of your trig function values. The sine of 0 is, in fact, equal to 0. All right, what else would be a good choice to plug in for x? If you said pi over 2, I say yay. We can certainly plug in, pi over 4, pi over 3, pi over 6, those, but let's stick to the easy ones that we know are going to have nice integer valued answers. That will make it easy for us to plot on our graph. Okay, so what is the sine of pi over 2? The sine of pi over 2 is positive 1. Next, we can plug in pi. So we end up with the sine of pi, which is 0 again. If we plug in 3 pi over 2, the sine of 3 pi over 2, we're at the bottom of the unit circle, right? So our y value would be negative 1. And then let's plug in 2 pi. What is the sine of 2 pi? Well, we're back on the right side of the unit circle, and that would be 0. If I kept going, what's going to happen here? So if I plugged in, let's say, 5 pi over 2, I would get 1. If I plugged in 3 pi, I would get 0. And if we kept doing that, these values are just going to repeat over and over again, right? Because all we're doing is going round and round and round the unit circle, and we know that those values, those y coordinates, are just going to repeat every time, right? Okay, so what kind of function does that make y equals the sine of x? I feel like I want to play Wheel of Fortune with you. You know, it's my favorite game show. Having trouble spelling today. All right, so what kind of a function is sinusoidal, or y equals the sine of x? It is indeed a periodic function. Because again, for every certain number of x values, those y values are repeating over and over again, right? So let's look at what our graph looks like. So 2 pi, I'm just going to split this up into the increments so that what we used here as our x values. And then the highest we go is positive 1, and the lowest we go is negative 1. And I think we kind of talked about this at some point, we mentioned it, and that should make sense, right? If we're talking about a unit circle, then the largest y value we're ever going to have is positive 1, and the smallest y value we're ever going to have is negative 1. So all of our entire sine function should fit between negative 1 and positive 1 for those y values, right? Unless, of course, we have the dreaded T word, dun, 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 transformations, which we'll get to later. Okay, so we've got a point at 0, 0, pi over 2, 1, pi 0, 3 pi over 2, negative 1, and 2 pi 0. Okay, so that is one complete cycle of our graph. Okay, so remember, we could continue to plug in points. That was one trip in a positive direction around the unit circle. We could go in the opposite direction, right? We could go clockwise and have negative angle measures, and we could still continue to evaluate sine there. So if we did that, we know that we would have, this is negative pi over 2, negative pi. What's going to happen? Well, this would be here, right? Sine of negative pi over 2, we're down here, which is a y value of negative 1. And then negative pi is 0. And we would go on so on and so forth. So we could continue this pattern infinitely in both directions, okay? In fact, it does continue infinitely in both directions. We typically do not write arrows when we graph sinusoidal functions, because if we were to put an arrow, that implies what? That implies that that graph is going to continue going up towards positive infinity, or depending on where you're at, down towards negative infinity. And we definitely don't want that to happen, all right? So we know that this graph is going to continue infinitely in both directions, okay? So now that we've done this, let's identify some information. Let's identify our domain. Let's identify our range. And then let's talk about the amplitude and period of this particular function, since we know that it is in fact periodic. Okay, so let's start with our domain. What is our domain? Do we have any restrictions? Remember, we just said we can plug in values infinitely in both directions. So our domain, if we're using interval notation, would just be from negative infinity to positive infinity. Our range, again, we already talked about a little bit, right? We know that the smallest y value we're ever going to have is negative 1, and the largest y value we're ever going to have is positive 1. Again, if we're just talking about y equals the sine of x. Once we put transformations in, that changes, right? So our range is from negative 1 to positive 1. Again, remember the closed brackets because we are including those values. All right, what is our amplitude in this case? So based on what we said about periodic functions last week, we know that the amplitude in this case would be 1, right? Amplitude is half the total distance from the top to the bottom. Okay, and our period is, well, what's that shortest repeating part of the graph? We said that this, right, is one trip around the unit circle. Everything else is going to start to repeat. So our period then is 2 pi. Okay? Okay, so hopefully that's good for sine. Now we are going to graph cosine. Let's switch to a different color. All these colors make me so happy, especially when they're new. Let's graph y equals the cosine of x. So we're going to do very similar to what we did for sine, right? Let's make a table of values and plug some values in for x. Do we want to choose the exact same x values for to plug in for cosine that we did for sine? Absolutely, because they're values that were easy to evaluate. And again, it's one revolution around the unit circle. So let's plug in 0, pi over 2, pi, 3 pi over 2, and 2 pi. All right, if we plug in 0, what is the cosine of 0? Cosine of 0 is 1. What is the cosine of pi over 2? That would be 0. If you don't remember these, then I'm going to urge you to continue to study your unit circle. And I'm just doing this fast because, well, because you should know it. Cosine of pi is -1. Cosine of 3 pi over 2 is equal to 0. And the cosine of 2 pi, we're back on the right side of the unit circle again, right? So that would be +1. Okay, so what do you notice about these values in relation to what we have for our y values for sine? So the values themselves are all the same, right? Our values are either 0, 1, or -1, right? Because again, if we think about where we're at one of the quadrantal angles on the unit circle. And our x-coordinate has to always be either 0, -1, or +1. But it is very similar to what we have for our sine function, right? So let's graph it and see how it is similar and how it is different. So 2 pi, and then again, we know that we're just going from -1 to +1, right? Okay, so let's plot our points. So we have a point at 0, 1, pi over 2, 0, pi -1, 3 pi over 2, 0, and 2 pi 1. Oopsies, yikes. Yeah, bad graph, no surprise. All right, so our graph looks something like this, right? Okay, it's harder to see when they're two separate graphs. But one thing before I do that though, is again, remember this pattern would continue, right? So this point would be at 0, at negative pi, we would have a y value of -1. Oh gosh, I missed, I wasn't even close that time. This is gonna come down here, right? And the graph is gonna look like this, okay? So again, a periodic function. Let me take this and put that on top of the sine function so that they're on the same graph, because then I think you're gonna see something that's really awesome that may be harder to see when they're separate like this, especially since my scale is not even close to what I used up here. Okay, so if we graph cosine, we have a point at 0, 1, pi over 2, 0, pi -1, 3 pi over 2, 0, and 2 pi 1. So this is the cosine graph. Wobbly, sorry. Okay, so again, that's just one cycle, right? But what do you notice about that purple cosine graph that I just drew in relation to the sine graph? Are they the same? Well, they really are, right? Except for what? What's the only difference between the two graphs? Is a phase shift. You don't know what a phase shift is, so I got really excited about that, and you're like, great, what does that mean? In trig functions, we talk about horizontal shifts as phase shifts. So the only difference between the two is a horizontal shift. If we take that sine function, we would have to shift it to the left pi over 2 units for it to become the cosine function. Or you can think of taking the cosine function and shifting it to the right pi over 2 units to become the sine function. All right, which is why sine and cosine are together considered sinusoidal functions. Every sine function could be rewritten as a cosine function. Every cosine function could be rewritten as a sine function. Isn't that exciting? Some of you are rolling your eyes at me again. I know who you are. I think it's exciting. So let's, same thing, identify domain, range, amplitude, and period. Okay, so here's the thing. This should be really simple, right? If every cosine function could be rewritten as a sine function, does the domain and range change? Absolutely not. So we can still substitute any values in. So our domain is still all reals, and our range, unless we have a transformation, which we'll get to, is still going to be from -1 to +1. And our amplitude, again, is still 1. And our period is just one full cycle, which is 2 pi. Okay, so same for both sine and cosine, unless we add in certain transformations. Okay, so far so good, right? Fantastic. I told you this would be fun. All right, so now I'm gonna make all of this go away, and let's talk about some transformations. We're not going to talk about all of them today, but let's talk about some and how they affect both the equation and the graph. Ugh, this board is gross. I need to find someone to clean it for me I would say every day like at school, but once in a while at school. Maybe one of the boys will come wash it for me. That might be bad. Okay, so let's suppose I gave you an equation, y equals 2 times the sine of x. All right, so how does that affect our graph? Well, if we remember our transformations, we know that this 2 in front represents what? This is a vertical stretch, right, by a factor of 2. So if we take our sine function and we stretch it by a factor of 2 vertically, what's going to change in that graph? So does the amplitude change? Does the period change? Okay, so if you said this affects the amplitude, then that would make sense, right? Because we're taking our original sine function. Oh dear, that's really bad. Let's try that again. It's still going to be bad. I don't know why I'm doing it over again. But if we take our original sine function, yikes, which looks something like this, and we stretch it vertically, then whoop, what are we going to do? We're not changing it at all this way. We're just stretching it like this. That's going to make our maximum and minimum larger and smaller, respectively, and that's going to change our amplitude, right? Okay, and what if we had y equals 1/2 times the sine of x? How's that going to affect our graph? Well, we know that the 1/2 now is a vertical shrink. So we're going to take this graph and shrink it vertically. So how does that affect the graph? Again, still the amplitude, right? It's going to make that amplitude smaller since it's making the graph shorter in this vertical distance. What if we were to put a negative in front? Does that affect the amplitude? Absolutely not, right? All it's going to do is take our graph and reflect it over. If this is my x-axis, right? Let's pretend, and I were to reflect this, then it would just be, oh boy, yikes, like this. Does that affect my amplitude? Absolutely not. Does that affect my period? Nope. The only thing it does affect, though, notice that normally sine starts at the origin, goes up to the max, oops, goes back to the x-axis, goes down to the minimum, and then back to the x-axis, right? If I reflect it over the x-axis, then instead of going up to the maximum first, it's going to go down to the minimum, and then it'll go up to the maximum later, okay? All right, so that a value, or that constant that we're multiplying the function by, is just going to stretch or shrink our graph vertically, and that will affect the amplitude of the function, okay? What happens if we put a number in front of x? So what happens if we had y equals, and this is true for both sine and cosine functions, right? I'm using sine as my example, but again, sinusoidal, sine, or cosine, it doesn't make a difference. What if we put a number in front of x here? So if we had any one of these, for example, all right, I could keep going with a million examples, right? Okay, so we know in each case that this number in front of x is what? Is going to be a horizontal stretch or shrink, right? This is a horizontal shrink, as is this one. And then the 1/3 x would be a horizontal stretch. Okay, so if we are stretching, or let me redraw that sine graph again so we can see that. So our sine graph originally looks like this. If we stretch or shrink our graph horizontally, does that affect the amplitude? Absolutely not. What does it affect? It affects the period. So instead of one full cycle fitting from 0 to 2 pi, if we take and stretch or shrink that, it's either going to take less space, so our period will be shorter, or it's going to take more space, so our period would be larger, okay? All right, so let's make some generalizations then. So let's say that we had y equals a times the sine of bx, or y equals a times the cosine of bx. Okay, again, remembering that sine and cosine are both sinusoidal functions. All right, so let's come up with a definition for our amplitude. All right, what is the amplitude of either of these functions equal to, based on what we just said? Okay, so our amplitude is affected by that vertical stretch, right? Is that entirely correct? Hopefully you're yelling, no, it's not. What's one thing that we need to fix about this? So we know that the amplitude must always be what kind of a number? You are correct. The amplitude has to be a positive number, right? Because it's half of a distance, and a distance is always positive. So to make that happen, we're just going to put absolute value, okay? So we know that if a is negative, what's really going to happen? So if a is negative, then the graph is just what? It is just reflected over the x-axis. Okay, so the actual amplitude is just determined by the absolute value of a, and then that negative is just going to reflect it, all right? Okay, what is the period? Usually we call it the fundamental period. I'm too lazy to write that, so this will be the only time I ever do that. And usually we just write period because, well, mathematicians and we're lazy. But the period, or the fundamental period, is what? Okay, so can we come up with an expression to represent the period of a function? So for our original sine or cosine graph, our fundamental period was 2 pi, right? Because this was one full cycle here at 2 pi. Okay, let's think about if we shrink it horizontally. If we have a horizontal shrink of 1/2, then we're going to take this whole graph and it's going to fit into half of the space, right? So if we were to do that, then if this is pi, we should have one full cycle that fits. Can I draw? Well, we all know the answer to that. Nope, see? Okay, so it should fit like this, right? So if it's a horizontal shrink, instead of fitting from 0 to 2 pi, one full cycle will fit in that interval from 0 to pi. If it's a stretch, let's say by 1/3, that means we're making it 3 times bigger. Our period would have to be 6 pi, right? Because we're making it 3 times as big, so 3 times 2 pi would give us that period of 6 pi. So where does that come from? Well, we're starting with our original period, which is 2 pi, right? To come up with this period of pi, what did we do? Well, we started with 2 pi and we divided by that value of b. So our period is simply 2 pi divided by the absolute value of b. Again, b could be negative, but if we think back in terms of transformations, what does a negative here in front of the x do? That negative is just going to reflect it over the y-axis, right? So it doesn't affect the period, it's just a reflection. Okay, so can we make a generalization about whether the period is getting larger and smaller for certain values of b? So let's suppose that the absolute value of b is greater than 1. If it's greater than 1, like these two, it is a horizontal shrink. And if it's a horizontal shrink, is our period getting larger or smaller than 2 pi? It's getting smaller. Okay, if that b value is between 0 and 1, the absolute value, then it is a horizontal stretch. And if it is a horizontal stretch, then the period is larger than 2 pi. Okay, so far so good. I say to myself because I'm the only one here. Okay, so let's do a couple examples, shall we? So the key here to graphing these, and they're really not hard at all because you don't have to do any plugging in or any work really. We need to remember that original 5-point pattern when we graph those original sine and cosine functions, and then as long as we can find the amplitude and period, we're going to be good to go. All right, so let me give you an equation. Let's identify the amplitude and period, and then maybe we'll graph it too. I don't know. Let's see how we feel. All right, so let's say y equals -5 times the sine of 3x. All right, so let's start by identifying the amplitude. We'll identify the period, and oh, what the heck, we might as well graph since we're here, right? It's fun. All right, so let's start with the amplitude and period. I so desperately want to say right now, who can tell me what the amplitude is? And then, depending on which class it is, either people are all shouting it out or everyone's just looking at me. So what is the amplitude of this function? This will be the one time that you can all blurt out answers and I won't yell at you to be quiet. The amplitude here is 5. Again, remember the negative does not affect the amplitude, so our amplitude is just 5. And the period of the function is, we know that period is 2 pi over the value of b, so our period is 2 pi over 3. Okay, so now that we know that, could we easily sketch this sine function? We absolutely could. This is probably a harder one to start with, but that's okay, we'll do it anyway. All right, so we know that if we go back, I don't know how well you can see this, but you can go back to your original sine graph if you wrote it down. This is what sine looks like originally, right? We start at 0, go to the max, we go to 0, go to the min, go back to the max, so that, or sorry, go back to the axis, so that it fits in one full cycle. All we're gonna do is change the scale and then draw those same 5 points, okay? That's all we're doing. So all we really have to do is remember this shape and then just figure out what our scale should be, okay? So we know that we're gonna start here somewhere at 2 pi over 3. So that's gotta be one full cycle of my sine curve. All right, now I'm going to divide this in half, right? Because originally, remember, it's 2 pi. We divided it in half and got pi, divided that in half and got pi over 2, and then the one in the middle here was 3 pi over 2. So we're essentially just dividing this into fourths. Half of 2 pi over 3, this will all be the hardest part, I promise. Half of 2 pi over 3 is pi over 3. Half of pi over 3 is pi over 6. So if this is pi over 6, this is 2 pi over 6, right? Which reduces to pi over 3, which makes this 3 pi over 6, which is really just pi over 2. So when you graph, you definitely need to have one full cycle labeled on your axis, okay? If you do more than that, it's fine, but you need to have one full cycle of the graph labeled on the x-axis, okay? All right, now we know our amplitude is 5, so our maximum value is going to be up at 5. Our minimum y value is going to be at -5. That's as fancy as we need to be with that. Okay, now let's graph. So we know that sine starts at the origin, right? Sine of 0 is 0. Okay, normally sine goes up, and back down. But since it's a negative in front, we know that it's going to be reflected over the x-axis. So instead of going up first and then down, it's going to go down first and then up. So using that scale, those are going to be the x values that correspond to those maximum, minimum, and 0 points. So we're going to go down to the minimum, up to 0, up to the maximum, and back to 0. And when we connect those, that'd be one cycle of y equals -5 times the sine of 3x. If we wanted more than one cycle, we could just continue that pattern, right? So then the next point here would have to be down at -5, up here. We could continue it in this direction as well. Oh, this is the graphing I know and love. Messy. So that looks something like this, right? And we could keep going in both directions. Okay, so does this change the domain of our function at all? Absolutely not. Our domain is still all real numbers. Does it change our range? Sure, we said the amplitude is going to affect the range, right? Because that affects how tall our graph is and how, so what the maximum is and what the minimum is. So our range then will be from -5 to +5. That would make sense? Okay, super. Let's do another. Let's do a cosine graph this time. Again, keeping in mind the general shape of cosine, right? So we know that sine starts at the origin, goes up, down, whoop. Cosine is going to start at the maximum, goes to the x-axis, down to the minimum, back to the axis, and back up to the maximum again. Okay, so that's our general cosine graph, right? Let's say we are going to graph y equals 1/3 times the cosine of pi over 8x. So let's identify our amplitude and our period, and then we shall graph. Okay, so our amplitude is 1/3. So we have a vertical shrink, right? Our graph is getting smaller vertically. And then our period is going to be 2 pi over b, so 2 pi over 8, which just becomes 16. Okay? All right, so let's graph. Okay, so we have an amplitude of 1/3, so we know we're going to need to go from -1/3 to +1/3, so I'll put that scale on the y-axis. Our period is 16, so I'm going to start by marking off a 16, and then divide this into fourths, right? If we divide it in half, this is 8. Divide the 8 in half, we get 4. So this will be 4, 8, 12, 16. Again, remember you need to label one full cycle. Okay, now we're going to graph our cosine function. So it's a positive. So if it's a positive coefficient, then we know we're going to start at the maximum and then go down. If it were a negative coefficient, it would be reflected. So we would start at the minimum and then go up instead. Okay, so we're going to start at our maximum, which is whatever our amplitude is. Then we'll go down to the x-axis, down to the minimum, to the x-axis, back up to the maximum. That is one full cycle. If we wanted more than one cycle, again, we could just continue that pattern in either direction, okay? And it doesn't matter which way. If I said to graph 2 cycles and you went to another cycle in a positive x direction, fine. If you went another cycle in a negative x direction, fine. If you went partway in negative and partway in positive, as long as it's 2 full cycles, it makes no difference where your 2 full cycles are, okay? Just as long as you have one full cycle labeled on the axis, okay? Okay, so what is our domain? Again, domain is not changing. That is all real numbers. And our range is affected by our amplitude, right? So our range will be from negative 1/3 to positive 1/3. Okay? Okay, awesome. Let's do one more problem, and that is going backwards. So if I give you a graph, can you write the equation of that graph? So let me get rid of this, and then let me check and see how good my, I was going to try and draw it, but I think for all of our sakes, well, let's see what I can do here. Sorry, you know that the graphing is the worst thing for me. Let me see if I put this up here, if this is going to work out well or not. If you can see that graph, I might have to zoom in on that a little bit. So technical issues, let me see how that looks. Can you see that at all? Zoom in a bit. Move that over a bit. Okay, so hopefully you can see that okay. All right, so let's say that we're going to write the equation of this particular function. Okay, so if we're writing the equation, the first thing we want to do is, let's back up. Let's think about our general model, right? Is either y equals sine or cosine, or y equals a times sine or cosine of b times x. So we need to know the value of a, right? We need to know the value of b, and we need to decide, is it a sine or a cosine function? Again, remember, every sine can be written as cosine, every cosine can be rewritten as a sine. However, if we don't use the easier one, then we're going to have to include a horizontal shift, which does get a little bit messier. So we're going to talk about how we choose which is the easier one. Let's start with the amplitude in this case, though. So we know that A represents the amplitude, right? If we look at our graph, we are only, and I know it may be hard to see, but we're only going up to positive 1/2 and down to negative 1/2. So that means my amplitude is 1/2, okay? We need to know B, but in order to figure out B, what we really need to know is what the period is first, right? And once we know the period, then we can figure out B. So if we look at our graph, again, depending on where you start and where you end, doesn't matter, but I'm looking at this from the minimum to the minimum. So that would be my period, right? So that cycle is fits from 0 to 2. So that means that my period is 2 units. Okay, now remember that B is really, the period is really 2 pi over B, right? I'm not even going to worry about a negative being there because I can write it without doing that, and it just will make life a whole lot easier. So I'm, for this purpose, just going to use 2 pi over B, okay? So 2 pi over B has to equal the period, which is 2. Now all we have to do is solve for B, right? So if I multiply both sides by B and then divide by 2, B is just pi. Okay, so now I know B and I know A. I can substitute those in, right? So y equals 1/2. We're going to come back to our trig function times whatever trig function, sine or cosine of pi x, right? Okay, so let's decide if we're going to use sine or cosine. Again, thinking about the original shapes of both of those two functions, right? Remember that cosine, we said, starts usually at the maximum and goes down. So that's the cosine of x. I might have zoomed us way out of that. And then sine is this one. So here's the key. Does the graph start at the origin or not? If it starts at the origin, it's going to be a lot easier. And when I say start, I mean, is there a point at the origin? If there's a point at the origin, then it's going to be a whole lot easier to use sine. If there is not a point at the origin, then we're going to use cosine. Okay, so in this case, is there a point at the origin? There is not. So let's use cosine as our function. Oops, I already did the pi x. All right, so we've got 1/2 times the cosine of pi x. Is that correct, though? Well, again, remember, cosine starts usually at the maximum. Does this graph start at the maximum? Nope, it starts at the minimum, which means that our graph has to be reflected over the x-axis. And to show that, I just need the negative in front of my equation. So that positive 1/2 would really be a negative 1/2. Okay, so hopefully that makes some sense. I know that was hard to see because I zoomed in and then didn't realize I was off the screen. But so again, you're finding your A and your period, using the period to find B, deciding whether it's sine or cosine, depending on whether you have a point at the origin or not, and then simply see if your A value needs to be negative depending on whether you start at the maximum. If it's sine, you go up first, or whatever the case may be, okay? So you'll have an opportunity to practice these on your homework assignment, and then in the next lesson, we will look at translations. So how is the graph affected by both horizontal and vertical translations, okay? So good luck with your practice. If you have questions or need help with anything, as always, feel free to reach out to me at any time. All right, have a great day, you guys.